Welcome everybody to part 2 of my talk on rhythm games. So today we're going to be talking about a few developments I figured out in terms of making rhythm games in Godot and how to make them feel good. And this is explicitly about enthusiast-grade rhythm games. Now what enthusiast-grade means is, serious rhythm games like Osu, DDR, Stepmania, those games that people play competitively, at least to a degree, that you want them to be consistent. This is not about games like Friday Night Funkin' or Love Live All Stars, which are casual games. Those are fine, but this is not what we're doing here. So, you may be wondering, who are you? Well, my name is Alex. I am from Spain, and I make a rhythm game called Project Heartbeat in Godot. It's semi-successful and it's going well, and it's my main source of income, so, it's quite fun. I'm very stupid. This is a big disclaimer. So please, anything I say might not be true, and it might even be completely wrong. I'm just going by what I figured out from my experimentation with audio stuff. Again, might not be correct, but, this is what I figured out, and it seems to be working now, so, I used to develop racing simulator software, so I have some experience making real-time stuff. Unfortunately, I got fired because I called my boss a cunt. To be fair, he was a cunt, but anyways. Now, this is an update on my previous talk that I made some time ago, I don't know, maybe a year ago? So you should watch that, because there's some information that I'm going to omit here, because I don't want to repeat myself. Now, what the hell is a Project Heartbeat? This is Project Heartbeat. It's a rhythm game with a big focus on user-generated content with user-made songs and heavy focus on the community, right? It's a clone of a game called Project Diva. Obviously the gameplay, as with all enthusiast rhythm games, is dependent on timing being right. Well, I say all, I mean all except Guitar Hero and Rock Band. Well, Rock Band is much better than Guitar Hero, but we're not gonna get into that. And please buy my game, because Mr. Vladimir Putin decided that, it's a good idea to invade a country and make gasoline expensive, and I need gasoline, so... Anyways, obviously the main focus of an enthusiast-grade rhythm game is chasing the last drop of latency, right? The Godot stack sucks for this, at least. It's pretty good. It's nice, but could be better, and it certainly could be better for this use case. We have to do something about it, because, we promised people a good game, and we are not delivering. So, the first thing you do when you find a shortcoming in Godot is you try to make it yourself, right? That's one of the beautiful aspects of having an open source engine, right? Unfortunately, the problems that Godot has are architectural, and they are much harder to fix by yourself, and they require a lot more work than you are probably willing to put in. So, for most games, Godot's default audio stack is good, but for this case it's not very good. We don't have a scheduled playback. There's no properly consistent way to sync our gameplay to the music. Because obviously in a normal game you are syncing to the high precision clock, but here you are not. You are syncing to the audio, so if they get out of sync, you're screwed, and the game is gonna get out of sync and it's all gonna suck. This actually happens in some commercial games, like Project Diva. Project Arcade, but that's an arcade game, so it's, very controlled environment, so it doesn't really matter. But yeah, that's one of the issues you will find. There are some other issues that I don't really understand, and I don't know why they happen, and they're too complicated to explain in a presentation, but it's too complicated for me, because I'm not an audio engineer, right? Either way, I tried a few things. The first thing was interpolating the hardware clock, sorry. You can get the hardware clock position, and with hardware clock, I believe Godot's documentation means the currently mixed audio position. So this is possible, and you can use the main thread delta to interpolate it when it changes. Unfortunately, I tried it and it doesn't work, so, to the next thing, right? The other thing the other naive thing I did was, okay, so we have to single-thread the audio, and this is one of the issues with Godot. Mixing happens when Godot wants it to happen, not when the audio driver wants it to happen. So you sometimes find issues with this, and especially on Windows, this is horrible, and it gives you a lot of performance hiccups, so it's not very good. So I thought, hey, let's put it in a single thread, right? That way we can ensure that it's probably perfectly synced. But it doesn't really work, because, if we're doing it on the main thread, we have to do it at some point in the main loop. And if we're doing it at some point in the main loop, it's gonna take 16 milliseconds between calls, which is how long a frame takes at 60 frames a second. So this is terrible. Doesn't work. Don't do it. It's trash. Because the way most audio drivers and most audio systems work in operating systems is by having a asynchronous callback to a function, and that's where you do your mixing and all your stuff. So at this point I thought, hey, Godot's audio engine is clearly not designed for this purpose, so let's try to find an alternative. And I thought about Bass, which is the library that Osu uses, and it's apparently very good. So, it's battle tested, hey, it works in other rhythm games, so might as well use it, right? It's fucking expensive, it's very expensive, and it's way more than a small game like mine can afford. So at this point you think, hey, what's my solution? What can I do? Well, let's go nuclear. Let's write our own audio engine. The problem is, we have no money, we are lazy, and we are Spanish, which is arguably the worst part of this. And you can see on the right a image of a Spanish satellite that got lost. To be fair, that was the fault of the Ariane rocket, or the whatever the fuck it was using, but it's still very Spanish to do something very complicated and then have something else fucked up. So anyways, I found this library. This is Miniaudio. It's an amazing C library, and it achieves amazingly low latency. It's stupid. I don't know how or why this happens, but it's very good. So, let's just get rid of Godot's audio system and write our own. How hard can it be? Well, when looking at Miniaudio, it has some very nice features, right, that we can make use of. We have an actually synchronized clock, because it uses proper synchronization primitives that are quite nice. And you can fire and forget sounds, which is not something that you can do in Godot. In Godot, you have to create an audio stream player. In Godot 2, you could fire and forget sounds, but you cannot do that anymore. And this is obviously very useful for stuff like, graphical user interface and sounds that are only played once in gameplay. It has a scheduled playback, which is very good, and it's one of the things we wanted. And there's a composition graph, which is similar to how Godot handles audio buses, so that's very good. Now, you have to set this option in your device configuration. It was in Miniaudio to get the low latency mode on Windows. Very important. And you can set the video size in milliseconds to something smaller than 16 milliseconds. Or the lower you set it, the more probabilities that you will get low latency. But the operating system may decide that you will only get a audio buffer that's a certain size, so you cannot trust this to be the actual buffer size. Now you have to implement the data callback if you're running on Windows with low latency mode. So that remember to do that. Set the performance profile to this. I don't know what it does, but probably helps. And ignore the STP boardbits implementation. There is a liborbits and libogg implementation in the repository for Miniaudio that will work much better. So use that, because STP boardbits was very good at the time, but it crashes on perfectly valid OGGs, so it's gonna be a pain in the ass. Now, this is our audio engine. It's called Shinobu, and it's named after this nice blonde vampire. It's the audio engine I made. It's made in C++. It's engine agnostic, but I have an implementation for Godot. It doesn't use nodes. So it fits much better with the workflow of a rhythm game of this kind. One trick you can do is use the dummy audio driver in Godot to disable Godot's default audio driver, so that you can slowly replace it with the new audio engine, which in this case is Shinobu. Now here's a trick I learned. This is a trick I learned from StepMania actually, and it's called priming the audio decoder. What this means is you will stick to a position. Let's say you are playing from second 1. You stick to second 1 and then you start decoding, but you don't play it back. Right? This way, when you start playing, you already have a buffer of already decoded music. So even if you have a hiccup or a fade slowdown, it will be enough for the user to not notice the issues. Now, obviously priming takes some time, so you have to find a way to hide it without stuttering or anything. How do we do it? Well, you have to resort to very old tricks in the book. For example, Project Heartbeat plays this very nice animation when you start playing a song. That's enough time to prime it. If a game has video, you can actually use the same technique for video decoding, so keep that in mind. Now, how do we deal with big buffers like this? Because one of the problems you will find is, if you have a big audio buffer, let's say you have a 20 millisecond audio buffer, it will only be updated once every 20 seconds, and that's bad. That will make the gameplay stuttery if you are timing the notes based on the audio position, which you should, by the way. So you will find this problem, right? So what do we do? Because, you know, our frame time is 60 milliseconds, and if we're getting updates every 20, that's out of sync. So some frames it will be updated, some frames it will be behind. So what do we do? Well, one of the options is using the no fixed size callback option in Miniaudio. So it has an internal buffer that's smaller. But this is losing performance for the sake of losing performance. You don't gain performance by doing this. In fact, you lose a lot of performance by doing this. And it's still not smooth enough because it's never gonna be in sync. Some frames the update might be slightly late and you will not be able to see it. So, we are gonna interpolate it. And how do we interpolate it? Well, this is a Shinobu clock. It's a very simple thing. It uses the standard library high precision clock. Disclaimer, if you're using Visual Studio 2012 or lower, high precision clock is aliased to system clock, so it's not gonna be precise enough. In that case, you should use Chrono Steady clock, but past PS 2012 is gonna be the same. On GCC and on Clang, it's perfect already, so you don't have to do anything. So as you can see on the right, when we are doing the mixing on the MA data callback function, we measure the current time after the samples have been mixed, right? And then when we are actually playing the song, we will be adding the offset, the time that it has taken since we measured it and until now, to the position of the output of the playback position. This way it's interpolated and it's very fast and it's very smooth, and this is the key to make this very good, and this will ensure that your users will have good performance, or rather smooth performance, even if they have some strange setup. The only problem is there's a kind of latency you cannot get rid of in this situation in high buffer sizes. It is the playback to when playing instantaneous sounds like note hit sounds and stuff like that, you cannot do anything about that because the buffer size is at least the size it is, right? So it may take 20 milliseconds for the next mix callback to be called, and that's bad, but there's nothing you can do about it. It's better than nothing. So obviously you should always strive to have the lowest buffer size you can, but if you can't, this is a very good second option. So I had to re-implement a bunch of effects from Godot. The spectrum analyzer, I re-implemented it, basically copying the code from Godot. It works the exact same way. It's used in Project Heartbeat it's used for the background, but I might expand it to be used in the UI at some point in other parts of the UI. So that's that. Now, pitch shifting, same thing. I didn't want to do this, but Lino told me to do this because the editor apparently uses it. So what this allows you to do is to change the playback velocity of a sound without changing the pitch, among other funky effects. So that's something you should definitely have in some cases. And so far we've tried Shinobu, and it's public. The source code is public. You can get it. It's on our Godot fork. Obviously, you can try. You can do whatever you want. It's a lower level than Godot's default, but it's good enough. So, what have we learned today? Well, making an enthusiast-grade rhythm game is hard, and it's gonna be very technical endeavor. So, I only recommend this if you are brave or if you are very stupid like I am. And please buy Project Heartbeat. I need money. Either way, Shinobu has been a great addition to Project Heartbeat. It's basically saved the game. A lot of people were having issues. A lot of people were having problems with stuttering, with inconsistent frame times, and other things. And apparently, Shinobu has fixed it. And not only has it fixed it, but it has also improved stuff like battery consumption and CPU times. So, it's overall very good situation. It's worked very well. So I recommend that if you are making a rhythm gaming Godot, like an enthusiast-grade rhythm gaming Godot, you should use either Shinobu or something like that, or make your own implementation based on Miniaudio or something, because Miniaudio works fantastic. Either way, that's all I have for you today. If you have any questions, I will answer them. I hope you guys have a good time and keep working.